Welcome to another lecture and module of Python and matrices course. In this lecture and module, we will be basically focusing on covering implementation concept of vectors and matrices and implementing them in a Python programming framework. We have learned a lot of different operations, a lot of different computational techniques in the domain of matrices and vectors previously. Now let's focus on how do we implement them using Python programming languages. In this lecture and module, we will be mainly focusing on various different operations such as matrix operation, vector operations, and solving a set of linear equation using Python. And then towards the end of this lecture and module, we will also focus on covering concepts of eigenvalues and eigenvectors and computationally solving these problems using Python programming languages. So again, in nutshell, what we are going to do is focus on implementing various concepts that we have learned previously in the previous set of lectures and modules using Python. So let's get started. The first thing that I want to mention and probably repeat is the file that you see, Python file that you see on the screen. I have opened it using Google Colab. As mentioned in the first lecture, I typically save my Python files in a Google Drive and then use Google Colab to execute, run the files that you have. It saves a lot of overhead, and I have encouraged you to use Google Colab. So that's what we have done here. What you see is basically a file open in Google Colab, and we will be executing various functions in the Google Colab environment. So with that, let's get started. The first thing that I want to discuss is the basic matrix multiplication or dot product of two different matrices. So what you see here on the left hand side, you have two matrices A and B. The A matrix has it's essentially dimension 3 by 3, and the B matrix has a dimension of 3 by 2. And we want to take a dot product of these matrices, right? So essentially, if you want to do that using Python, you have to call the numpy library that needs to be called, and you can use the function dot of the numpy library to execute it. And there is another way to execute. Recently, in the recent version of Python 3.5 onwards, you can also use this @ operator to do the dot product of two different matrices that is out there. Okay, and the method that or the code that I have listed here, and this is something that I will also post for you to the notebook so that you can refer to this, uses both the approaches that we have. Okay, so what we do is first we begin with importing the numpy library in the current environment, which is basically the Google Colab here, and then giving it as an alias np. So that's the first line of code: import numpy as np. np is the alias for numpy, and the reason we do it, rather than writing numpy, we can write np, and essentially that will be a shorter version to write numpy. So that's what you will see. That's an alias that we call it. Okay. So first thing that we do is we define a matrix A, and in order to define the matrix A, we use this np.array command. So what you see is np.array, and then you see the numbers 2, 5, 3, 7, 2, 8, 7, 4, 2, and so on. Now, what these numbers represent, the way we enter the data in np.array is we essentially provide the data row-wise. Okay, so if you look in our matrix A, the matrix A, the first row is 2, 5, 3, the second row is 7, 2, 8, and the third row is 7, 4, 2. So if you look into how we instantiated the matrix A using np.array, we have the first row, which is 2, 5, 3 under the square brackets that we have. That denotes the first row, and then we have comma between the square brackets that denotes that we are beginning the second row, and then we enter all the elements of the second row. So if you look into the matrix here, the second row is 7, 2, 8, and similarly you have the after the initial 2, 5, 3, you have 7, 2, 8, and then following that you have 7, 4, 2. So this is how you can initialize a matrix inside Python using a numpy library. Similarly, what we have done is we have also initialized the matrix B okay? And recall the matrix B has 3 rows and 2 columns, and that's why the initialization is there, okay? So again, this is the way to input. And then as I mentioned, what you can do is you can use the multiply matrices, which is A dot, and then in the in the round bracket you can put the second matrix, which is in this case is B, and that will be the one way to implement the matrix dot product in Python using NumPy. Or the second one you can use is that at the rate operator, right, which is listed here. Here we are doing this D is equal to A at the rate of B, and if you do that, that is also a way to multiply two different matrices and take the dot product of those matrices that we have, okay? So we have executed this command and we printed both using C, both the types, like A dot parenthesis B and also D as A at the rate of B, and you can see the A and B matrices are supplied here, and the product A dot B using the two approaches comes out to be same. So these are the two different simple ways to implement matrix multiplication or dot products in Python library that we have. Now let's move on to the second concept. The second concept that we want to discuss is the concept of determinant. So if you have a matrix and if you want to take the determinant of a given matrix, then how do you carry that out using a Python, right? So first, similar to what we have done, first you need to define a matrix. So we have defined, for example, the matrix that is here. We, even though we want to take the determinant of the matrix, we need to define this matrix itself. And as you can see, we have again used np.array to, instantiate a matrix A, which has first row of 2, -5, 3, the second row of 7, 2, and 8, and the third row of 7, 4, -2, and that's what you can see in the code here. Yeah. And then what we do is basically we call this, the function det in square parentheses. What you can see is np.linearalgebra.det and round parenthesis A. This is the command that you can use to compute the determinant of the matrix A that is out there. Okay, so let's execute this. And if we execute this, you will see the A is defined here, and the determinant, which is defined by A underscore det, right? The value which comes out to be -380, that is what the determinant value of the matrix that you see here. So this matrix, the determinant of that is essentially equal to -380 plus so on. Okay, so this is how you can compute the determinant of a given matrix. So let's move on to another concept. Now we typically end up doing a lot of matrix inversion. So given a matrix A, you want to find A inverse, which is A to the power -1 denotion. And in NumPy, essentially there is a function called INV, or short for inverse, in the round bracket that you can use to take a inversion of a given matrix. Okay, so let's say we've defined this matrix A, which is right here, okay, and we want to invert that matrix itself. So the first line of command that you see on the left hand side is essentially defining this matrix A, which you see right here, which has the first row 2, -5, 3, the second row 7, 2, 8, and the third row 7, 4, -2. Okay, that's what we define using A equal to np.array, and in the round bracket, and then we have square bracket, which in each square bracket we are listing the elements related to the first row, and then moving on to the second set of square brackets, we are listing the elements of the second row, and so on. Okay, and then once we have defined the matrix or defined matrix A, then if you want to take the inverse, the command that we will be essentially using is this np.linealg.inv or in, and then in the parentheses we will supply the matrix A, which we have defined above, and that will help us in basically taking the inverse of the matrix A. So A underscore inverse will be essentially storing the inverse of A, and the command that is used to do this is right here. Okay, so we can go ahead and you can execute this. So you can see the A is defined by here, which is 2, -5, 3, 7, 2, 8, 7, 4, -2. Those are the elements of A, and we take an inverse of this, right? We have the one that is taken by. Now we know that if we take an inverse of a matrix, okay, and then we multiply that matrix by itself, then that should be essentially an identity matrix, right? So that's what you see right here. This the set of command that you see on the top. That's what we are trying to identify, right? So we have taken the inverse of a matrix A, which has been stored in the variable A underscore inverse, and then we are taking a dot product of that with the original matrix A itself, and hoping that that will be very similar to the identity matrix. So if you look into the value that has been printed out in the I, in the diagonal elements of that, you will see the entries are 1, and in the non-off diagonal elements, the entries are very, very close to 0. So this is another way of verifying that given a matrix A, if you multiply that matrix A with its inverse, that will lead to an identity matrix. So this is a computational way of verifying that identity that we have. Okay.